Okay, the fourth week we're going to talk about distance finding in using raster data. And there's a lot of aspects of this. Probably some of the coolest but most frustrating or difficult to understand aspects of using raster calculator. And so a lot of this will not be on the exam. I really will concentrate on the first three pieces, but there's a couple things that would help you maybe have a little quicker process on the exam. So I'm waiting for ArcGIS to load, so hang on one sec. So what we're talking about in this section is the idea of Euclidean geometry, so running straight line formulas in the first two exercises. And then in the second exercise where Euclidean distance doesn't work, so maybe you have a mountain in the way and Euclidean distance would not make sense, or you've got a huge building or some expensive land parcels. So when we're talking about Euclidean distance, we're talking about the distance from some kind of source cell to the distance from some source cell to every other cell in in the raster data set. And the interesting thing about the Euclidean distance is we will start out with, I'm going to start with the allocation one for a second. You're going to start out with no raster data at all. You're going to start out with a shape file or feature class that has, I think, 8 hospital points. And what you're going to do then is set your environments. And this is where that becomes really critical, because when you set your environments, you indicate how big you want your grid cells to be and what is your input for creating a raster. And so your input in that first exercise will be the hospitals, and you want to create an allocation raster which will give you 3 raster outputs. And so what it will do first is create a grid with those points as their target areas or their focus points, and divide the raster into allocations or sections. So which area, which raster is closer to which point. And so what you find, you'll get it will automatically display in this thematic way or categorical way, and you'll see that all of the grid cells here are closer to this source point than any other of the source points. So once I know that, then what I want to create would be a direction. And so the Euclidean direction says if I'm going in a straight line, which direction do I need to go to get from that cell to the source point? Actually, I think it goes the other way. I think it goes from the source point to the cell. And so the source point has a direction value of 0. If you went straight north, that would be 360. If you went due west, that would be 90. Due south would be 180. Due east would be 270, and then all points in between. And then it creates a distance raster, which is this one that we did first. And it says, okay, so if I'm standing at this point, how far, if I go in a straight line, is the center of that point? How far is the center of that point? And it gives you the distance in the allocation, not from every cell. So if I only had one source cell, I would get a distance value for every single cell in the raster. So when you run your allocation, Euclidean allocation, or your, you get 3 outputs. One is the allocation, so which cell is in which allocation or section. Then you get a distance, so each grid cell, how far is that cell from that particular source, and then you get a direction. So in the exercise, I can't tell if I can delete that. Ooh, no, I can't. Okay, hold on, let me go back. In the exercise, you're going to create your raster around these hospital points. You're going to give it, I think it's 100 by 100 foot grid. And the idea is to understand from schools which hospital is the closest. So the allocation tool will give you all three. This is also the tool that's used if you want to do not just horizontal distance but vertical distance. And what actually gets created is this raster file. You're not going to see it like this because it will be symbolized based on some standard symbolization, whether you're doing allocation, distance, or direction. But I just kind of played with it so you could see that each one of these little dots is a grid cell that's 100 feet by 100 feet. And if I open up my attribute table or my properties for that raster, I get the information about the size, how many columns and rows, and I could scroll down and find the horizontal units, etc. Now, the linear or the vertical units are sometimes difficult to tell, and so the exercises took you through some different ways to determine what were the vertical units. And I can look at on a DEM, but this is not, just ignore what I just said. I wish I could erase this. But anyway, that's when you're looking at a DEM, you want to find out the vertical units because that's relating to elevation. For this, you don't have elevation. Okay, so moving on. Exercise 1 is going to ask you to create this 1 meter or 100 foot grid cell raster. But then what it gives you is this, let me see if I've got that one up, distance 1. Yeah. What it gives you is feet in floating point, and floating point means there can be an awful lot of decimals associated with that, and it makes it really difficult then to kind of interpret easily and quickly the data value. So I'm going to open up which one am I doing? My miles, my distance to hospital. So hold on a sec. Open up that table. So here we go. I'm going to open up so you can see this is 4,086 point blah, blah, blah feet to the hospital. So if I open up my properties, and running this tool makes it really hard to see that. I don't want to open up the properties. I want to open up the attribute table. The attribute table is grayed out, okay? And you cannot see the attribute table of a distance of a floating point raster. Later, when you convert this to integers, you're going to be able to look at the attribute table. So anyway, I've got this really crazy feet number, so you're going to convert that to miles, and you're going to use I don't know if you use the raster calculator. You'll have to walk through that. Oh, you're going to reclassify and group the mile ranges. Oh, that's it. You're going to use the divide tool. So you're going to open up in the raster analysis tools and find the divide tool. And the divide tool will take the feet divided by 5,280, and you will get a new raster that you should name miles, distance in miles. So here we go. There's my distance in miles. And again, I've got crazy decimals, right? So you're going to take those distance in miles and then reclassify them. And I did that 2 different ways so that the values actually are whole numbers. And when I look now at my attribute table, I can see how many schools are, or how many areas are 8 miles from the hospitals. That's the first part of that. Okay. Then you're going to run your direction, or look at your direction because you've already run that. And one of the things you want to do is reverse the compass direction. So instead of saying to the hospital, you want to say from the hospital. And I may have that reversed, but you'll read that in the directions. So right now your directions are to do greater than 0. We don't want to include 0. So we want to add 180 degrees to all of those values that are from greater than 0 to 180, because we want to flip them. Actually want to rotate them 180 degrees to show that instead of going to the hospital, we're going away from the hospital. And then anything between 180 degrees to 360 degrees or greater than 180, you want to subtract 180 degrees because you want to flip them to the other side of the compass. We want to leave 0 alone. And the reason for that is that 0 means no direction. And so that's your source, right? So you have 8 hospitals. You should have 8 or 9 hospitals. We could actually count that. Hold on, I'm looking at my attributes here for hospitals. And it says, let's see what it says. There's 9 hospitals. Only you can't see that because that table's freaking huge. Oh, wait. Can it do this? Maybe I can do it this way. This silly. There we go. Yeah. So I have 9 hospitals. So I'm going to end up with 9 0 values that I don't want to change the value. So I played around with the map, with the math, just to make sure I understood what was happening. And then they have you enter what's called a con statement. Now, the tricky part here is in the example, if you copy and paste that, they're assuming that you named your raster the exact same name in the example. So I think they called theirs distance to hospital. If you named your raster something else, you need to make sure you type that in the con statement where it names the other raster. And you can usually use the menu at the top and just select your raster and add it into your statement, or you can type it in. But if you type it in, you want to make sure that you have the brackets which indicate a folder. So basically the condition statement says if the raster value is greater than 0 and the raster value is less than or equal to 100. So if it fits in that category, then you're going to add 180 to that raster value. Okay? And the comma means the then. So that it goes to the first value and it looks to see if it's true. And if it's true, if it fits this, it goes ahead and makes that change. But if it's not true, if it's larger than that, I'm going to go back here, there is a second condition statement which says, okay, if that's not true, look at it this way. If the raster is greater than 180, then you want to subtract 180 from that. And then this comma 0 pretty much indicates, and if it's 0, leave it alone. Okay? And so that's the condition statement. So that's one way that you can change the values in your raster. The third and fourth exercise in this lab look at the weighted distance. Okay, so again, the straight line may not be the best. There may be impedances, which they call costs. And so what you want to do is find the least cost, and this is set up to find the least cost. And somebody the other day asked, could you find the heaviest cost or the highest cost? And absolutely. And that just depends on how you name your values. So basically, let's say I have a DEM and I have created a slope, and I also have a raster that I've created that shows me average snow depth, right? So what I want to be able to do is to combine these two and find so let's say I want to build a road. So I want to find the least average snow depth, and I want to find the lowest slope, because that's going to make it a lot less expensive to build my road. And so what I want to do is reclassify these original rasters, which are floating point, into some kind of common classification system. So where 1 is good and 9 is horrible, right? So I may not be able to get all of my first choice, but I may be able to have some first choice slopes and some first choice snow depth, but I may have to get a couple high snow depths, so that but really low slope, which would make no sense at all, actually. Anyway, but that's kind of the idea. And so you have to come up with a classification system that works for you. And in the in the exam, the answer for that is based on the knowledge of somebody else. I don't know why they chose that one, and I don't remember reading that anywhere. But anyway, so this is what you would do. So if slopes under 10 are good, then I'm going to categorize. I would reclassify as slopes 0 to 10 is the new value is a 1. Slopes 10 to, I don't know what they've got here, 10 to 11, the new value is 2, on up like that. And you can do that just by hand reclassifying, because we did that in one of the earlier labs, or you can reclassify from a table. One of the things we've gotten in class are a couple script errors running the reclassify by a table, and the solution to that seems to be close ArcMap and start again. At home I had to actually reboot and start again, and then the script ran fine. Okay, so now we're looking at the cost surface, and one of the things that's really cool is that now I can combine these two rasters because they have common values that can be added, and the addition of them means something. In vector analysis, we kind of did intersection. So where one layer overlaid another layer, that was my prime values. So here's the cost surface of the slope plus the, what was the other thing? Snow depth. And if I add them together, values of 2 are my prime location for my road. Values of 3 aren't so bad, 4 aren't so bad, 16, 18 are pretty bad. But maybe if I ran my road up the 2s, why would I do that? Ran the road through the 2s, down through the 8, the 16, and then the 18, I might have actually overall the least cost. The example they have in the exam or in the tutorial is once you get your combined raster, you want to run the least cost from 2 features. So basically in the example I have a power point and a source, and I want to run a power line based on the lowest cost in slope, in elevation, in land use, whatever attributes they've given you. And so I can see that I have to start here. I don't have an option because that's where my power plant is. I can go here to 1, 1, go to 2, up to 2, and then I'm going to have to be stuck with a couple 9s. But if I ran just straight here, actually it seems like it would be a whole lot shorter. But anyway, oh no, because I'm starting at 5, 9, 9, 9. We could add that up. But anyway, but that's the idea. So the workflow, one of the questions asks you about the workflow. And so in this example, you started with the DEM and you derived several rasters, 2 rasters from that. And then you used the land use and you reclassified your land use. And I don't remember if that was a raster to begin with. It might not have been. If it isn't, if you've set your environments and create a raster from that polygon, then those lines will match up really well. So anyway, I have my reclassified slope, I have my reclassified land use. I'm going to use the plus tool or add those together and get my total cost. And then I'm going to run 2 mystery files, the cost distance and the cost surface, that will give me my least cost path. Okay, so one of the things they ask in the exam again is what is a backlink raster, and I did a lot of researching on that. Basically all I can find is that the backlink raster gives you some values of 0 to 8, which is the direction from each cell, and it's used in the calculation of the surface. And one of the things I think it says in that lab is this is really difficult to understand, so move on to the next, and I was plenty happy to do that. A lot of this is black box, you're just trusting the algorithm and the programming that it's doing it right. But then I think it's really valuable when you get your output to go back to this and make sure it makes sense. Did it run correctly? You can't just trust that everything you inputted worked, because you might have had a wrong value somewhere. So it's always good to kind of see if it makes sense to you. Here's an example of reclassifying a categorical raster. So I have data that has very different kinds of land use, and I might want to say I want them in a 1, 2, 3 so that values 1 are where I want to build a park, right? And then the reclassifying of a continuous raster looks at this floating point, and so I'm going to get very detailed information, and really what I want is just 1 mile, 2 miles, and 3 miles. It's much easier to kind of look at that value.